Hi everyone, my name is Ning Pan Tin. Together with my team members, today we will be introducing a critical challenge in smart energy system, managing building energy safely and efficiently using deep reinforcement learning. This is the content that we'll be discussing today. Before I start, have you ever wondering how much energy does a building consume? As we move forward to a greener and smarter city, buildings stand at the forefront of energy challenge. They are responsible for over 36% of global energy consumption and around 37% of carbon dioxide emissions. That's massive. So naturally, optimizing how buildings use energy is not just about cost savings. It's essential for climate actions. However, energy efficiency alone is not enough. People spend nearly 90% of their times indoor, and most of them stay at home. So any control system we design must not only be energy efficient but also ensure thermal comfort and safety. For example, keeping a room temperature within a comfortable range. Traditionally, control strategy like rules-based control, RBC, use thermostat and PID control, which is easy to apply, but they are often reactive and rigid. Then bring us to our next method is model predictive control. Uses mathematical models to optimize decision in advance, which is efficient and safer, but relies on complex and accurate models. And that brings us to our new method, which is reinforcement learning or DRL. Unlike MPC, DRL doesn't need a precise model. Instead, it learns by observing, acting, and improving with the environment. But DRL also have a downside. It explodes. Means that it will explode to unsafe conditions, and in our case, overheating a room or stressing a HVAC system. And that's our solutions, safe DRL framework. Instead of relying on DRL framework alone, it combined with MPC. We'll see how this framework opened up a new path forward. Now I will pass to Wei Tao.
Thank you, Kantian. My name is Wei Tao. Now I will start with the existing challenges. First, the data dependencies and computational costs. Some approaches will require large amount of training data and high computational demands. Also, some approaches will have the poor computational efficiency due to the absence of an analytical form of the value function. Then the second one is the physics and constraint handling. Some articles will lack of physical knowledge because of relying solely on data-driven methods. On the other hand, some will be overly conservative. Then this makes the limiting of the operational space and also the potential opportunities. The third one is dimensionality and practical implementation. Some methods will unable to handle high dimensional continuous space data, so that maybe need additional components in hybrid mode. Then this is the limitation of RBC, MPC, and DRL when used alone. RBC is often lack of the flexibility. MPC will be model dependency and computational burden, and DRL will be lack of safety guarantees. There are some safety concerns in DRL due to exploration behavior. First, DRL agents explore various control actions during learning. Second, no theoretical guarantee that safety constraint. Third, particularly risky in real-world energy systems. And the last one is complicating the safety check due to the absence of analytical value function in DRL. After that, the need for integrating learning-based and model-based control. The safe DRL synergizes the DRL that used to explore optimal control decisions under uncertainties, together with MPC that utilize as a safety filter to check online. DRL action will be rejected and the conservative MPC action will be adopted if unsafety is detected. Then the last is the objectives of proposing a hybrid DRL framework of DRL and MPS. First, this can create an implicit safety set at each step, then enhance the system robustness. Third, the model will enable to train parallelly. And the last is to propose a safety metric as an indicator to quantify the safety performance of algorithm during test period. Now I will pass to Song Hao.
Hi everyone, I'm Song Hao. Today I will talk about a novel approach to a safe and efficient building and energy management for the safe gateway performance learning. And managing energy in building is crucial for cost reduction and migrating climate change, but it's equally vital to ensure occupant comfort and health. This creates a complex challenge as traditional control methods have limitations. And the safe DRL framework addresses this by synthesizing deep performance learning DRL with a model predictive control MPC. And the DRL is used to explore optimality and learn optimal behavior in uncertain environments. It's powerful for finding efficient control strategies. While the MPC serves as a real-time safety filter to dynamically ensure constraints are met. It uses a model to predict future states and verify safety. And the core design leverages the strength of both SDRL as well as the performance optimization, while the MPC provides a safety net. This framework can use the off-the-shelf DRL tools and even approximately building models in the MPC for efficiency. And here's a quick algorithm overview. And the first, the DRL agents propose an action, and the MPC safety filter simulates a system future behavior over a prediction horizon if the DRL action is applied. If the simulation predicts that all future states remain within the predefined safety sets, like the temperature limits are confirmed, the DRL action is applied. And if any future state is predicted to be unsafe, the DRL action is rejected, and the MPC on optimized safe action is applied instead. And this process dynamically creates an implicit safety set, avoiding the need for a complex implicit definition. This also serves as a fallback mechanism. And to quantify the safety performance, a comprehensive safety matrix is proposed. It consists of two aspects of constraint violation. The first one is the unsafe time ratio, which is the duration of the violation, defined as the ratio of the time the safety constraint is violated relatively to the total process time. And for the buildings, this is the percentage of the time the temperature is outside the comfort zone. And the next one is the severity ratio, which is the severity of the violation, characterizing the deviation of the unsafe state from the constraint. For buildings, this is the maximum percentage deviation of the temperature from the upper or lower limit during the test period. And the total safety matrix is the sum of these two metrics. And next, the tests conducted on a high fidelity building models show that the safe DRL framework significantly enhances the constraint certification and improves the performance to MPC and baseline controllers, demonstrating its ability to balance exploration for optimality with dynamic safety assurance. And this is achieved with a relatively small computational overhead, taking a maximum of a few seconds per step. And in summary, the safe DRL combines the learning power of the DRL with the constraint following of MPC, providing a robust and safe approach for a complex system like building energy management. And that's all for my part.
Okay, thank you, Song Hao. Hello, I'm Justin. We are reviewing a test case used in this research paper that focuses on building energy management. The author utilizes the Vestas hydronic heat pump test case, which simulates a single zone dwelling in Belgium. It includes various dynamic models, controllers, weather data, and pricing schemes. The house is occupied by a 5-member family with a 12 by 16-meter floor area, 2.7-meter ceilings, and a south-facing windows. During winter, the heating demand is around 80 watt per square meter. So the simulation uses the bulk test environment, which provide various measurement and control variables such as control signal U, electric power P, thermal power Q, and indoor temperature T. And occupancy is defined as before 7 a.m. and after 8 p.m. for weekdays, while all days for weekends. The thermal comfort range is around 21 to 24 degrees Celsius when occupied and 15 to 30 degrees Celsius otherwise. So the emulator will test 2 heating periods, which the first one, typical heat days, which is from January 17 to 31st, and the second one, peak heat day, which is from April 19 to May 3rd. And there will be 3 pricing schemes to be considered: constant, dynamic, and highly dynamic. So the heating system will consist of a 15 kilowatt air to water modulating heat pump with a 3.5 kilowatt power consumption connected to a floor heating system. A PA controller is used for initialization and benchmarking. Lastly, the paper will compare 3 RC thermal models used to stimulate building thermodynamics in Bob tests. First order RC model consists of one resistance that represents heat transfer between the ambient temperature and the zone temperature. One capacitance that stores thermal energy is used for quick simulation and basic control testing. The second order RC model consists of 2 resistance and 2 capacitance. It represents the building envelope as a separate thermal mass. This adds more realism by simulating heat flow through the walls before reaching the indoor air. Third order RC models adds an internal thermal mass and more resistance for inner walls or furniture. It is the most ideal model for testing advanced control strategies. This model will allow for different levels of accuracy in capturing building thermal behavior and supporting robust control strategy evaluation. That's all for my part. Thank you.
Thank you, Yashin. Greetings to my lecturer. My name is Yang Cheng. So I'll be presenting about the MPC and DRL implementation. So let's start with the MPC setup. The first step is developing a thermodynamics model of building using RC model to simulate how heat flows through the building and affect zone temperature. ambient temperature, and cashback heating power. This is as you can see here, this is the mathematical formulation formula. Here, the T zone is the zone temperature, the Tm is ambient temperature, and the QHV is the heating power, among other terms that represent various heats, gains, and losses. Next, this is the cost function, which minimizes both energy cost and thermal discomfort to optimize system performance. This is the cost function formula, and the goal is to maintain the zone temperature near the set point while minimizing energy usage. Then the system operates within temperature constraint. For example, the zone temperature when occupied must cap between 21 and 24 degrees Celsius, and when unoccupied, it will cap between 15 and 30 degrees Celsius. In addition, the heat pump control is limited to 0 and 1 to ensure realistic operation. And finally, the hyperparameter tuning such as horizon and control step size is critical. The author set prediction horizon to 3 hours and the performance and the control step to 15 minutes, balancing performance and computational efficiency. Moving on to the DRL setup. The state space includes zone temperature, ambient temperature, and solar radiation. The action space represents heat pump control from 0, which is off, to 1, which is full power. For DDQN, it's discrete, and for PPO, it's continuous. Then the reward function encourages energy efficiency and thermal comfort. The agent receives the reward for minimizing energy cost and maintaining the desired temperature. The formula is as follows. Then the author used DDQN for discrete action space and PPO for continuous. Other algorithms like A2C, SAC, and TD3 are also tested. To speed up the training, the author used OpenAI Gym with parallel environments, which this allowed multiple bot test instances to run concurrently, reducing training time. That's all from me. I'll pass the time to Jason.
Great. Thank you, Yao Chen. My name is Chu Jason. I'm going to present the comparison between the 4-controller PI, MPC, DDQN, and safety DRL across 2 scenarios, which are peak heat day and typical heat day using the Bob test environment. On the peak heat day, the MPC maintains much better safety. The unsafe time ratio was 0.012 versus 0.093 for the PI, and overall safety metrics was 0.016 for the MPC versus 0.096 for the PI. Although PI used slightly less energy and had lower cost, the MPC improved thermal comfort dramatically. On a typical heat day, both controllers performed worse due to the high ambient temperature, but MPC was safer and more consistent, which remained at 0.041 compared to the PI have the value of 0.09. Now let us look at the comparison between the DDQN and safety DRL. The safety DRL achieved perfect safety and comfort on the peak heat day, which are 0 discomfort and 0 violation. On the typical heat day, it still outperformed all others in cost and emission with a comfort score of 0.13 kh, which is much better than the DDQN. They proved that the MPC as the safety filter effectively eliminated unsafe action from the DRL and improved overall performance. Now let's look at the system behavior of the MPC controller. For the first graph, we can notice that the MPC always maintains the indoor temperature within the comfort zone consistently, while the PI overshoot or undershoot the temperature limit. In the middle panel, the MPC control signals smoother and align better with the heating demand and electricity price pattern. For the system behavior of DDQN controller is highly volatile. On the typical heat day, the DDQN frequently fails to maintain the temperature within the comfort zone, especially when the solar radiation spikes. For the safety DRL controller, it preserves DDQN energy saving behavior when safe, but use MPC as a filter to avoid violation. This is why temperature trajectory is more stable and control signals are smoother compared to the DDQN. In a summary, safe DRL combines the optimality of DRL with the safety of MPC. It consistently outperforms the standalone controller. It ensures comfort, energy efficient, and safety even in dynamic weather conditions. That's all from me. I'm going to pass the time to Wen Yao for the conclusion. Thank you, Jason. Hi, everyone. My name is Wen Yao, and now I'm going to be talking about the conclusion part. Firstly, the author has presented a hybrid DRL plus MPC framework that filters any unsafe action to guarantee 0 comfort violations. They implemented a parallel Bob test training pipeline to benchmark 6 RL algorithms over 10 million steps and identify the best. And lastly, they also introduced a composite safety metric capturing both the duration and severity of any temperature breaches. Next, Figure 15 has illustrated this in action. The red dashed line shows the raw DDQN outputs, while the blue bars show the final safe DRL actions. On a peak heat day, the MPC filter intervened 686 times and accepted 658 DDQN actions. On a typical heat day, it intervened 950 times and only accepted 394. This shows how the MPC filter steps in when the raw DRL alone would struggle under variable conditions, proving its worth. Next, let's take a look at the three key benefits. Firstly, safety. In peak heat tests, unsafe time and severe violation ratios were both zero, whereas a standalone RL agent violated comfort over 30% of the time. Secondly, performance. Across 2 weeks of simulation, energy costs matched pure MPC within 4% while reducing the cumulative thermal discomfort by 75% compared to a basic PI controller. And lastly, practicality. Safety filter adds only about 2.6 seconds per 1 hour decision. And Docker-based parallel training cuts the wall clock training time by roughly 60%. Lastly, let's take a look at the future work. First, multi-zone expansion, by applying the framework to buildings with interacting zones and actuators. Next, robust safety filters, by incorporating uncertainty bounds and sensor noise into the MPC step. Thirdly, sim to real deployment by using staged hardware in the loop and human in the loop trials to bridge emulator and live operation. And lastly, broader objectives by optimizing humidity, indoor air quality, and renewable energy integration for full-scale multi-objective energy manager. That is all from our group. We're happy to take any questions. Thank you so much.